So welcome back. Now we are moving on to part 2 of massive parallel processing. It's Apache Spark. It's actually MapReduce, but better and faster and everything and more generic and so on. So it's really using all of the lessons from MapReduce with an even better system. It's not the only one, right? There's other systems around, like you will be able to learn them very quickly if you know Spark. So remember where we are. We did a lot of things already. We are more than halfway. It's roughly half of the semester. So we processed the data. We've looked at MapReduce, which is this idea of mapping, then shuffling the data around over the network and then reducing. We saw the architecture where we have the job tracker collocated with the name node and the task trackers collocated with the data nodes, because we bring a query to the data. But now we're going to focus on a few issues that basically are a bit annoying and that the engineers actually solved. So some of the issues, just on a very high level. The job tracker, so the process running on the coordinator node, basically has too much to do. It has to do the resource management, knowing which machines there are, how many task trackers, the memory they have, the CPUs they have, and so on and so on. It has to schedule the whole thing, like tell the task trackers to process what task and so on. It has to monitor, and when it detects that there is a machine that failed, it has to reallocate it to somebody else, maybe restart the machine, and so on and so on. It has to take care of the job life cycle, meaning that detect that all the map phase is done, then it can be shuffled, and then the reduce phase is done, fault tolerance, and so on and so on. It's just too much for the same process. And a typical limitation, at least back then, now it's probably changed, but back then when we run into the issues, there were scalability issues. Like as soon as you reach something like 4,000 nodes, things started not breaking, but kind of to be too slow. And the same goes for the number of tasks. We could go all the way to 40,000 tasks, but it was difficult to go beyond that. So that was the first issue. It was the scalability. The second issue is the bottleneck, because there is so much going on right there that this can at some point be so overwhelmed that it blocks the whole thing. Imagine like now, thousands of machines there, and it's just this one process that has to take care of the thousands of machines. This is just, this is a bottleneck. And as computer scientists, you're probably trained to spot the bottlenecks and the single points of failure. So this is also another issue. Issue number 3, I kind of already told you, but basically we have too much of the job tracker. It's the expression like jack of all trades, master of none. It basically both schedules and monitors, and we would like to actually separate them. It would be nice if we could have separate responsibilities on the scheduling and on the monitoring of the job, right? Now, another issue has to do with what I told you about the fact that we assign to the slots, whether they are a mapping slot or a reducing slot, we do it ahead of the MapReduce job. And that means that during the map phase, the reduce slots are all idle. They're just waiting, because you cannot start reducing until the map phase is completely done, right? Because you need all the key values for every call of the reduce function. So basically, we have a good part of the cluster that just remains idle while the map phase is going on. And the same goes during the reduce phase, that now it's the map slots that remain idle. So this is not very efficient, and it would be nice if we could have something a bit more dynamic than that. And this is why Yarn was invented. So of course, as soon as you see some abbreviation that starts with YA, you probably guess it means yet another, just like YAML is yet another markup language. And Yarn means yet another resource negotiator, right? So this is a piece of technology that is solving these issues. But the very nice thing about Yarn is that it solves the issues not just for MapReduce, it's actually very generic. And in fact, Spark is going also to rely on Yarn. So basically what happens is that MapReduce was re-implemented as a version 2 of MapReduce that doesn't use the job trackers and the task trackers, but instead of that, it relies on Yarn. So I just would like to quickly introduce Yarn to you. I used to spend 2 hours on that, but we no longer do that because it's more physical, it's a bit less relevant. But another reason is that Yarn is not fully well documented. So there's a lot of as soon as you try to dig deeper, there's a lot of open questions that are hard to figure out. So I really, to confuse you less, keep it on a high level. The first aspect of Yarn shouldn't surprise you too much because it's yet the same architecture with the coordinator node and worker node. So the coordinator node has a process called the resource manager, and that's the same machine where you also have the name nodes, the H master, and the the job tracker, but actually not, because we're replacing the job tracker with this. But this is the idea. And then on the worker nodes, together with the data nodes and the region server processes, we now have the node manager processes, right? Now, what are these containers? They look like blocks, right? But this has nothing to do with HDFS blocks. Containers are some sort of logical abstraction for resources. It means for amounts of memory, a number of cores, and so on. So we abstract away all of the virtual cores available for compute and the working memory, the RAM available there. It's all logically handled as containers. Maybe this container has 4 virtual cores and 10 gigabytes of memory, and this one has 5 or 6 virtual cores and 20 gigabytes of memory, and so on, right? So it's a logical abstraction of booking resources, blocking resources, right? You could almost view them like virtual machines. It's not exactly it, but it's almost like this. Like you can allocate resources and then run virtually. It's just as a very coarse analogy, okay? So what happens with Yarn is that the client can submit a job, for example, a MapReduce job, but it can be something else than MapReduce. And then the resource manager is going to receive the job, and it's going to say, okay, I'm going to schedule resources for you, but I'm not going to monitor your job. I'm delegating that. Delegating is a very good thing. So the resource manager takes one container, switches it on, and promotes it to being an application master. And now this application master is going to take care of orchestrating the whole MapReduce job. So you see, we nicely decoupled the allocation of resources from monitoring the job that is now being delegated to this application master right there, right? And then the application master is going to react by saying that, hey, I'm not going to run this MapReduce job alone, right? I need resources for that. So the application master is going to connect back to the resource manager and say, now I need 1,000 containers in order to do my mapping phase and so on. So he's going to ask the resource manager for more containers, and the resource manager is going to give to the application master these containers, and now they can be used to map, to reduce, and so on. But the nice thing about it is that the application master doesn't need to ask for all of them at the same time. It can, for now, only ask for the containers it needs for the map phase, and later, when it sees that the map phase is almost completed, it can start booking the reduce containers, right? So this is all dynamic, and now we are no longer wasting the resources that we don't use. But now you might be wondering, but yes, we are still wasting resources. It's just that we have not asked for the containers yet, but the containers are still there. But the key to understand is that you're not alone using the cluster. Typically, the cluster with thousands of machines belongs to a company that has thousands of employees, and you might have 20 employees using the cluster at the same time. And they're each using part of the resources of the cluster, but you're not the only one. So it means that all of the containers that have not been booked, they are not necessarily idle. They might be used by other people, right? And when these other people are done, it frees up the resources and so on. So what we are optimizing here on the high level is the use of the cluster. We try to have many people, and then the resource management is about spreading the resources across all of the people who use the cluster, right? Okay, and now we can forget about the rest, because once we have the application master that kind of does what the job tracker used to do for the monitoring, and then the containers do what the task trackers used to do, then we basically are back to what we know about MapReduce, right? For whom is that clear? How we separated the resource management from the actual orchestration of the job. Now, about the resources on a high level, what do we care about for resources? Well, at ETH, especially in the systems group, there's a lot of people doing hardware stuff. I'm not a hardware person, so to me, hardware is something that is very abstract. Even there's a lot of very interesting research going on the hardware side. It's also very important for data science. But what I understand from the database perspective is that we have some memory to store some data, intermediate data. We have some CPUs that do the computations. We have the disk to store more permanently, and we have the network to communicate across machines, right? So if you think on a very, very abstract level, this is what the hardware is. This is what the resources are. And so typically when you allocate the containers or request containers, you typically ask for that and that much memory and this many CPU cores, and maybe this part of the disk bandwidth and this part of the network bandwidth. Now, what is done is this part. This everybody knows how to do, requesting memory and CPU. Disk I/O, network I/O, seen as resources. Maybe they made some progress now, but last time I checked, it was work in progress to also expose them as resources, right? But from a high-level perspective, it's these four. Okay, so now what we have is the resource manager that takes care of scheduling the resources and managing the applications. And then we can have multiple application masters. It might be that there's 20 people running MapReduce jobs on the cluster, and they each one of them has an application master that booked their own container. So now you see, it's called multi-tenancy. We can have multiple people co-using the cluster at the same time. The idea, and this is a bit similar to HDFS, so that shouldn't be too much new to you, but there is this idea of, again, sending heartbeats. So the node managers send regular heartbeats to the resource manager to say that they're still there. And then the resource manager is keeping track of the nodes that are still running. And if at some point it stops receiving heartbeats, then it's going to assume that the node is no longer available, and then it will just stop allocating resources from that node. Okay. What's important is that the resource manager couldn't care less if a map slot crashed. It just couldn't care less. That's not the problem of the resource manager. It's the problem of the application master, right? So the resource manager just says, here's your resources and so on. So it's not responsible for restarting anything upon failure. It's just scheduling things and allocating resources. It's the application master that does all of this. Furthermore, the application master, what's actually running in that container depends on the application. MapReduce is one example. It could be the MapReduce brain for a job, but it could be Apache Spark, it could be MPI, and so on, right? So there's plenty of other possible application masters, and anybody can implement new ones, right? So it's all agnostic, basically, to the application that you use. So the application master is supposed, and that whoever implements an application master is supposed to take care of that. It monitors the containers for failure, and if there is a failure, it's going to reallocate in order, for example, to re-execute a mapping task if it fails somewhere else, right? So it's relaunching the containers if needed, right? So again, I'm a very high level here. I'm not entering into the details, but now what happened when people use the cluster, you have multiple strategies for allocating the resources. The most naive strategy you have is there is a person that has the entire cluster, and when they are done, then there is another person that takes over the entire cluster. It's called FIFO, first in, first out. So you just have a queue of users and they just use the entire cluster. But of course, then you don't have multi-tenancy, right? Because it's always one person at a time using the cluster. So obviously that's not the best way to do it, which is why what's done in practice is that you start having a strategy of utilizing the cluster. For example, imagine a university with a cluster, and they might decide in some high-level executive meeting that the mathematics department gets 40% of the cluster, the physics department 10%, and the computer science department 50%, for example. Then you might even plan strategically based maybe on costs or budget or whatever. This is the plan, basically. It's like who gets what from the cluster. And then Yarn is supposed to implement that and actually allocate the resources more or less following that. So when you start doing this, organizing with some sort of strategic plan of who gets what, then you can start partitioning the cluster. And at any point in time, you might have that part of the cluster that goes to some queue, for example, the computer science department, and this other part of the cluster that goes to the mathematics department, right? So this is called capacity scheduler. This was a FIFO scheduler, capacity scheduler. And then there is something even better, but very, very complex, that's called the fair scheduler. What the fair scheduler is doing is that if it notices that some department is not using the cluster at all, it's going to elastically reallocate to the other departments that are actually active. So the fair scheduler has a bit more elasticity, and it's going to keep increasing or decreasing the resources in a way that uses the cluster a bit more. Just to show you on one example, because that's a very good paper, it's called Dominant Resource Fairness. It's actually co-authored by some of the people behind the Apache Spark. I think back then they were at Stanford. It originates from Berkeley, but this was, I think, done at Stanford. The problem that this solves is how do you allocate resources with both looking at memory and CPU? If you only look at memory, it's easy, right? Imagine you have 1 terabyte of memory, and if somebody gets 10% of that, they get 100 gigabytes, right? So if you have just one dimension, it's easy. It's just a multiplication. But the problem is when you consider both the memory and the CPU. Let me explain. Imagine that Alice, for her mapping MapReduce job, she needs containers, many containers, but each container needs 30 gigabytes and 2 cores. Bob also needs some of the cluster, but his containers are different. Each one of Bob's containers needs 10 gigabytes of memory, but 6 cores. So you see that they don't use the resources in the same way, right? Bob is a bit more core intensive, CPU intensive, while Alice's needs are more memory intensive. How do you deal with this? Because it's not homogeneous, right? You cannot just do a multiplication and spread the resources, right? And there is a trick that actually works also from a game theoretical perspective, because it's an incentive for people to not overbook what they need. So it's very clever. What you look at for every person is what is their highest percentage. In the case of Alice, 30 gigabytes is 3% of the total memory. 2 cores is 2% of 100 cores. So for Alice, it's the memory that is important. It's the 3% of memory, which is greater than the 2% of CPU. For Bob, 10 gigabytes is 1% of the memory per container, but 6 cores is 6% of the CPU. And so as a rule of thumb, and this is highly simplified, what I'm telling you here, is that because of this, if you only look at this max number, Alice, if the strategy at the board meeting of the university was they get 50-50, then you agree that Alice should get twice the number of containers that Bob gets. Because one container by Alice, only considering this, is half of one Bob's container. So it's logical that, for example, Alice will get 20 containers and Bob will get 10 containers, right? And that way, every container by Alice uses 60% of the memory and 40% of the CPU, and 10 by Bob uses 10% of the memory and 60 of the CPU. We cannot go beyond that, because if you calculate, that's 40% plus 60% of the CPU, so the CPU is fully used. But we respected the ratio between the two. The number of containers here is twice the number of containers there, right? So they both use 60% of their dominant resource, right? 60% of the memory here, 60% of the CPU there, all right? It's just a curiosity. We are no longer, again, it's no longer part of the material to go into the details, but I just want to show you that it's not as trivial as it seems. That's really a very complex system that keeps getting improved. And it's fully generic, works with MapReduce, with, so that's Apache Spark. What I call this DAG distributed processing is actually Apache Spark. MPI, message parsing interface, graph processing also. So you see there's many different applications, all right? So we get, as a summary of Yarn, we separate between scheduling and monitoring. Now the monitoring is delegated to a container that is an application master. We are more scalable, more available, and we get multi-tenancy because it works with plenty of people using the cluster at the same time. And the second version of MapReduce actually is using Yarn instead of the job tracker and task trackers. All right, that actually brings us to Spark, because Spark is one of the next generation. It's not the same team. It uses Yarn as well, this resource negotiator. So let me start. There's 5 minutes left, so it's going to be high level, and then we'll continue tomorrow. What does MapReduce do? It maps, it shuffles, and then it reduces. But reducing is not very different from mapping, right? It's just calling functions in parallel. So I was a bit provocative here and said map, shuffle, map, right? So basically, in a job, we just map, shuffle, map, and we are done. And if you need to map, shuffle, map, shuffle, map, shuffle, map, you just need to have several jobs that you execute one after the other. It's a bit limiting. MapReduce is also limited to key-value pairs. You might remember that everything must be a key-value pair, so that's also a constraint that we have in MapReduce. Now, if I abstract that a little bit away from an abstract perspective, if this is like the entire input, we have a map phase, and then there's the entire intermediate data, then reduce, and then the entire outputs there. MapReduce can be seen like this, but you probably itches to generalize that. What if we just take any DAG? You know what a DAG is, right? Directed acyclic graph. So instead of just restricting ourselves to just mapping and reducing, let's just accept any DAG like this. The only constraint is that there are no cycles, no directed cycles. And every one of these rectangles here represents some collection of data. This one is probably the input. This might be some output. This might be some other outputs. But basically now we generalize to a DAG in terms of the data flow. This is essentially what Spark is doing. In that sense, it's a generalization of MapReduce because we support this. I have redundant slides there. And I'm going to end here just telling you that there's a name for these nodes in the DAG. They're called RDDs. Learn that by heart, RDDs, because I'm going to be saying that hundreds of times, RDDs. It means resilient distributed data sets. That's the name we give to all of these intermediate data sets and input and output data sets, right? So Spark manipulates RDDs. So let me just check, wait before you go, that you followed. You asked a lot of questions, right? So it was very good that we took the time to answer them in the first hour. And tomorrow, if you have more questions, I can also take some time for them. But just wanted to check how it feels, if I should accelerate, slow down. Okay, so far so good. So many of you are above 80%. Read the textbook. There is an entire chapter on MapReduce, right? So read the textbook. That should help a lot. Thank you very much for attending today's lecture, and I'll see you tomorrow at 9 a.m. for the continuation. Goodbye.